Today, in this new episode of the series on option Greeks, we're going to talk about gamma and theta. I was introduced to both terms by a fixed income derivative trader during an internship at an investment bank. I remember him juggling these terms, thinking I'd understand his strategy. Unfortunately, the reality was that I didn't have a solid enough grounding to follow a conversation with him. The aim of this video is to provide you with the keys to understanding these concepts so that you can feel totally at ease. Gamma and theta are two very important variables of a derivative contract. If I've decided to bring these two Greeks in the same video, this is because, as we'll see, they share a close relationship. As a reminder, the price of an option can be broken down using the Taylor formula. This formula simply explains that the overall variation in the option price is due to the variation in each of the factors that make it up. In the formula shown, you can see that each Greek affects the price of the option. Theta corresponds to this term and represents the variation in the option price with respect to its maturity. It just means that, even if every other term remains constant, the price of the option will still change due to the variation of its lifetime. For example, an option with a maturity of 2 weeks does not have the same price that an option with the same features on the same underlying asset, but with maturity of 2 days. On the other hand, gamma corresponds to the second derivative of the option price to the price of the underlying. As can be seen in the formula, the variation is squared, which means that gamma is a second-order derivative, whereas delta, theta, rho, and vega are first-order derivatives. The consequence of this second order is that its effect is hardly felt in small price movements compared with delta, but is important for larger price movements. In this video, in addition to the presentation of gamma and theta, we'll understand a rather classic relationship for options. Theta and gamma have opposite signs. Let's take the case of a call option. On this graph, we can see the payoff and the true price of the option. As you can see, the option price is higher than the payoff, and it is not a hazard if I represented the price of the option above the payoff. The reason behind it is the convexity of the call option. The convexity of the option can be seen on the graph by the skate ramp appearance of the curve and means that the derivative of the function is an increasing function. Knowing this, we understand that a long put is also convex because even if the payoff is decreasing, the derivative of the payoff is increasing. We go from a decreasing line of slope, -1, to a flat curve of slope 0. Going from -1 to 0 is an increase. This is why a long put is also convex. But you may wonder, why talking about option convexity? Well, because it's a property of options that is important not to overlook, and it has major consequences for the option price evolution and the sign of the Greeks. Convexity is a mathematical property that can be defined as the fact that, for every chord drawn between 2 points on the curve will never cross it. At worst, the curve and the chord will overlap. Intuitively, how can you quickly see if a function is convex? Let's take the example of the squared function. We see on the graph that the function decreases rapidly, then slows down and increases. We know that the growth of a function is defined by its derivative. A function with a positive derivative grows, and a one with a negative derivative decreases. The study of convexity consists in the study of the variation of the derivative. In our example, the growth of the derivative is constant and equals 2. To measure this, all we need to do is to derive the derivative, and we obtain the second derivative. In physics, if the function considered is a position, the value of its second derivative is called the acceleration. This is the variation of the speed, which is the first derivative. The link between this second derivative and convexity is that if the second derivative is positive for each x, then the function is convex. This is equivalent to say that the growth of the function never slows down, or that its derivative function is increasing. We can now apply this concept to financial options by using the variation of the payoff, or the option price relatively to the price of the underlying asset. In this case, the first derivative is delta, and the Greek that represents the convexity of the option price is gamma. Gamma is the second derivative of the option price relatively to the underlying asset's price. The sign of gamma indicates the convexity or concavity of the option price or the option strategy. Graphically, it's easy to see that when we buy a put or a call option, the payoff has a convex profile. But when we short the put or the call option, we are in the opposite situation, and the payoff profile becomes concave, the inverse of convex. To remember these signs easily, let's take two examples. First, in the case of a long of call option, you see on the graph that delta is whether 0 if the spot price is below the strike price, or 1 if it is above. Consequently, the more the spot price increases, the more the delta increases, going from 0 to 1. Delta being an increasing function of the underlying price, gamma is positive. Now let's take the case of a short call option. You see on the graph that when the spot price increases, delta goes from 1 to 0. Delta is a decreasing function, so gamma is negative. The profile of this payoff is called concave. Concave payoffs are those obtained when shorting a call or put option, and convex payoffs when longing a call or put option. Now let's understand why the convexity of the option price and the payoff explains why the price of an option is always higher than its payoff, and why the price of an option with a concave payoff is always lower than the option's payoff. Let's consider that the time value of the option is 0. To enter a contract, a buyer only need to pay the current payoff of the option. In this case, a convex profile means that the investor holding this option has more to gain than he has to lose. As you can see, in the worst case he gains nothing, but loses nothing either. And in the best case he gains an amount, which for a call is theoretically infinite, and for the put is at best the strike price. An investor in such a situation finds himself in a contract for which if the price were 0, it would always be profitable to enter and hold it. Absolutely always. This is why the real price is higher than the option's payoff. The option price reflects the balance between supply and demand to enter the contract. Even a strongly OTM call contract will generally not be worth 0 if it has time to mature. When you short a call or put option, you are in the opposite situation. The best you can do is gain nothing, and the worst is lose all your money. You have to remind that the real price of a convexity option is always higher than its payoff. Now that we understand gamma, what about theta? Theta is pretty intuitive too, and the explanation will not be very long. To understand theta, you need to understand what an expected move is. An expected move is, as the name suggests, the expected price movement that the underlying can make in a range of time. In the case of options, we deal with the expected move over the remaining lifetime of the option. This expected move makes it possible to predict, with varying degrees of certainty depending on our risk aversion, a value interval within which the price will end up at maturity if we make assumptions about the distribution law of the price. For example, considering the simplest and best-known model in which the price follows a normal distribution, we also say that the price follows a Brownian motion. We can then easily express the expected move with 68% confidence when considering just one standard deviation, and with 95% confidence when considering 2 standard deviations. The confidence interval shows that with a 95% chance, after the time t, the price will be in this range of values. Obviously, the values of the interval depends on the law you choose to model your price. But a closer look at this formula reveals an important point. The confidence interval widens with time. This first observation tells us that the longer it is before the option matures, the greater the chance of winning a high payoff. Reusing the convexity of long options, the longer the time remaining, the higher the expected move, both on the upside and on the downside. But the convexity cancels out the unfavorable movement. In the case of a call option, a sharp fall is not harmful, as losses are limited to 0. The same applies to a sharp rise in the case of a put option. The display shows price broadcasts for an underlying asset with no drift. The first shows a simulation of 500 trajectories for the price of this asset over a 10-day period. The second shows this simulation for a period of 20 days. Clearly, we prefer to buy an option with the latest possible expiry date. The more time left, the more we can hope for a strong price movement in the direction we want. we can see that the price reached in the second simulation is higher than in the first. The reason behind this is that the asset has had more time to reach a high value by increasing or decreasing randomly. These arguments around the expected move show intuitively why, when we go long a call or put option, the theta is negative, which means that the more time passes, the cheaper is the option because your expected move during the remaining life of the option decreases. And why in the case where we go short, the theta is positive. As you probably understood in these two explanations, theta is closely linked to the convexity, and therefore is closely linked to gamma. So let's link gamma to theta. Another property for understanding the sign of theta is that, as I told you in the video about delta, at maturity, the price of an option merges with its payoff. Once we know this, we have all the tools we need to understand the theta sign in any situation. In the case of a long call option, convexity means that the actual option price is always higher than the payoff, as we understood earlier. On top of this, we know that at maturity, price and payoff are the same thing. The only possible dynamic for the option price over time is therefore to decrease until it reaches the payoff. The option's time value becomes lower and lower, and the two curves eventually merge. The sign of theta is not independent. The sign of theta is a direct consequence of the sign of gamma. In a market with normal conditions, gamma and theta will have opposite signs. In cases where we have a concave payoff, we are in the opposite situation. For example, the profile for a short put is the symmetry by the x-axis of the profile of a long put. Therefore, the payoff is concave and the price is under the payoff. This difference between the price and the payoff can be interpreted as a risk premium paid to the seller of the option for the risk he takes. Nota bene, the determination of this risk premium is exactly what pricing models like Black-Scholes provide. We therefore understand the close link between convexity of the option price represented by gamma and the impact of time on that same price represented by theta.